So, Chuck, you've seen beautiful photos delivered from our space telescopes, Hubble and the James Webb.
Absolutely.
And they're these stunning colors. And have you ever wondered, like, is space really that colorful?
I thought that they had like the equivalent of a white dude with an afro at NASA who just stood and just was like, and now we're going to make a happy nebula.
They're the colors of the rainbow.
Right.
And can you recite them? Do you know them?
Red and yellow and green and blue and purple and orange and...
Okay, Roy G. Biv.
Roy. Red, orange, yellow, G, green, blue, indigo, violet.
There you go. Now, there's sensibly really only 6 colors there, but Isaac Newton had a mystical fascination with the number 7, and he labeled indigo in there between blue and violet. So we see these colors because we have sensors in 3 different parts of that spectrum in our retina. So we have a red sensor, we have a green sensor, and we have a blue sensor.
Right.
This is RGB.
Every television has it.
It's why that's the thing.
Right.
It's to match our eyeballs. Okay? So if you have red light, green light, and blue light, you can mix them in different ways and reproduce any of the colors in the entire spectrum.
Right.
If we go into the universe with our eyes, we would see the spectrum manifested wherever things are generating light. We would see red stars, white stars, blue stars. We'd see certain spectral features. However, our cones have a higher light threshold than our rods.
Okay.
So we have 2 ways of sensing light. One senses shades of gray from black to white. The other senses colors.
Right.
So one are the rods.
And cones.
The cones are the 3 areas of the spectrum where our retina is sensitive. All right. So here's the problem. If the source is not bright enough, no matter what color it is, it'll show up as gray.
Okay.
So in space, hardly anything that's so far away, hardly anything is very bright.
Right.
Your ability to see anything that's kind of underlit, it has to do with how many photons are entering the pupil of your eyeball. Now, you may notice that under dark conditions, the iris dilates.
Right.
And under very light conditions, it
They
constricts.
Right.
All right. And in fact, but that's that test is, are you dead or not? Where, they take a flashlight, put it over your eyes. If the pupils constrict,
right,
because there's plenty of light coming in, it doesn't have to stay open. That means some neurons are still firing in your body that otherwise looks dead.
They also do it to see if you have been doing drugs. That's more of a police thing, though. I'm just saying. Yeah.
I wouldn't know. So
Okay.
So your pupil will be like half a centimeter. So what's that? Like a fifth of an inch?
Right.
In diameter. The diameter of the Hubble is 92 inches. And so that's a huge difference in the size of the bucket the iris represents to collect light.
To fill up with light.
To fill up with light. So now here we go in other parts of the spectrum. So let's go to the infrared. Here's how you make a color picture with infrared. You ready?
Go ahead.
You get 3 bands within the infrared, the full infrared part of the spectrum. Infrared is very wide. In fact, it's much wider than what you did.
Right.
Okay? You get 3 bands, one on the left, one in the middle, one on the right of that range of light. Okay? Take pictures of the universe in those 3 bands of light.
Okay.
Because something might be giving a little more information in one band versus another. That's why something looks a different color than something else. I then have 3 otherwise identical photos taken through 3 different filters.
Right.
Now here's what I do. I slap an R, a G, and a B filter on those images. I take that light. It's photons recorded as infrared, but I assign these photons to blue, these to green, and these to red, and stack them together, and I have a full color photograph.
There you go.
That's how you make a full color photograph. You might not know this, but all color photography has a red, a green, and a blue sensor, where whatever it is that's detecting the light. It's a CCD.
Yeah, no matter what it is. Yeah.
No matter what it is.
Yeah.
And it's the merging of those 3 that gives you the full spectrum of light.
So when you're doing that with a camera, which all cameras do that.
Well, the film does it, yeah.
The film. But in a camera nowadays, it would be the sensor.
So is it false color? Is it fake color?
Right.
I'd like to think of it as shifted color.
All right.
It's the color we would see if our three cones were those.
We're able to see in that. Right. Yeah, exactly. It's that simple. If our three cones could see in that spectrum of light, that's what we would see if we were able to receive that information.
That's what we would see.
Right.
So I'm totally fine with that. And you can do that in the radio part of the spectrum.
Right.
Ultraviolet, it doesn't matter. You just need 3 bands.
You need 3 bands.
To give a concrete example here, one of the more beautiful images from the James Webb is the Carina Nebula.
Absolutely.
This is a relatively nearby region where stars are being born deep within.
Stellar nursery.
And you see structural detail. These are the narrow band filtering. That's the fruits of using narrow band filtering that shows you edges of things where precise phenomena are taking place. Molecules are forming, they're being destroyed, they're radiating, they're absorbing, this sort of thing. If you were there, if you were like right on location, you'd be close up, but the intensity would still be very low. And it would just be this low gray
cloud looking like
a cloud bank.
Right.
That's all it would be. That's all it would be.
Right.
So my field ain't nothing without telescopes.
Well, they see better than we do. So what's the big deal? I don't have a problem with it.
Yeah, okay.
You know, I mean, listen, I don't get mad at Navy SEALs when they put on night vision goggles to carry out a mission like, oh, what, you can't see?
Okay, so now here's where we get clever. You ready?
Mm-hmm.
In this gas cloud, there's a molecule that's giving off a single wavelength of light.
Okay.
Okay, so it's very narrow. If I'm going to look at that with a big wide band of a filter, it's going to get diluted with all the other light coming from other things happening in that gas cloud. So I'm going to take a very narrow filter, targeted exactly for that feature, and that's going to be one of my 3 filters.
Right.
And when I do that, the picture that comes out, you can see actual places in the gas cloud where those molecules are generating light.
Damn.
You are extracting resolution in the object because not all of the object is behaving in exactly the same way. And we can know what that is in advance, slap on the right filter, create the color photo, bada bing. They're veins of iron from an exploded star that are penetrating through this gas cloud that would otherwise look uninteresting.
Right.
So we're being clever about what we target with our RGB filters.
These filters are so much better than your Instagram filters.
That's right. I forgot. They all have filters. So these pictures that you see, they've done one of those 2 things. They either just slap the RGB in what we call broadband filters, or they're narrowband filters that enable us to see very specific detail within them.
That is amazing.
Oh, by the way, we can take these 3 filters in the infrared, put it in another part of the infrared. I said infrared is a very wide part of the spectrum. You put it in another part, and you see other things.
Right.
So this is the power of what's going on in all of that imagery. It all depends on what's giving you the light, and have your filters isolated that which is giving you the light. And then when you make the photo, it is manifest in all of its glory.
That is great.
So in other words, it's not what you would see in space.
Right.
It's what you would see if you had vision that was
in that spectrum. Right.
So false color
Yes.
is a very legitimate means of communicating statistical information.
Okay.
Because our eyes and brains are very good at picking out color.
Right.
For example, yellow and green are adjacent to one another on the spectrum. Roy G. Biv. Mm-hmm. If that were a grayscale, you would barely be able to tell the difference between those 2 colors.
Right.
Whereas because they are in color, immediately you can pick out a yellow from a green, even though astrophysically they are very similar in their properties. What you do is you take a color and assign it to something you want people to notice. You ready? Here's a weather map of a storm coming in. The red part is where it's raining. Is that red over your hometown? Then it's raining over your hometown. The blue part is where it's not raining, or maybe it's snowing.
Right.
You just start assigning colors to features of information that would not otherwise have a meaningful color to attach to it. That immediately tells the viewer, I see where the rain is. I see where the low pressure is. I see, like in the barometrically speaking, I see where all of this is happening instantly by looking at colors. That is not what we do in astrophysics.
Your weatherman is lying to you, people.
No.
Okay, that thunderstorm does not have any
Red rain in it.
red rain in it, no green rain in it, and no blue rain in it. Okay.
There's one fun philosophical point about colors. I'll end on this.
Go ahead.
We all have to agree that certain color names apply to the color that we assign it.
True.
We just have to agree. And then all other colors come from that. If I say, oh, this isn't red, this is more like salmon. Well, you go fish a salmon out of the lake and out of the river, and that's the color.
All right.
Okay.
Right.
Lemon yellow. We got to color. It's a lemon.
Yeah, we already know what a lemon is.
Okay. Orange. We know the color of orange.
We can see an orange.
Right. Sea foam.
Okay.
Eggplant.
Well, eggplant we can see. Yeah.
Okay. After you agree what the base colors are, which don't derive from anything, it's just a word somebody invented, all other colors derive from other things in the world that you know what color it looks like, so that you can reference it back to that original color.
Yeah, but then you get into areas like burnt sienna. Come the hell on. Really?
No. I've been to Siena, Italy, and if you look at the rooftops, that's burnt sienna.
Why? Because the houses were burnt?
Okay, sorry. It's sienna.
Right.
The rooftops are that color, and then you darken it a little.
Oh, okay, I see.
You get burnt sienna. I get there. No,
okay. All
you don't
right.
need abstractions to get that one.
All right. Okay.
You don't have a good example because one don't exist.
I'm trying to see if I can figure out a good example of a color that is an abstraction.
Okay, here's one. Coal black.
Well, yeah.
Okay.
Yeah, well,
coal black would be, I guess, a little bit non-reflective. It would be more muted.
Yeah, it's the color of Miles Davis.
Stop. On the black spectrum.
Yeah, it's on the yeah. It's Wesley Snipes. That's the color.
Right, that's where it goes.
Yeah.
Again, we're using adjectives to help out the modification of other words.
I'll accept that.
Okay.
That's good.
All right, we got to call it quits there, Chuck.
All righty.
Always good to have you, man.
Always a pleasure.
All right, Neil deGrasse Tyson here with yet another explanation of things. This one, the color of objects in the universe, where they come from and how we make them. Neil deGrasse Tyson, keep looking up.